Hey, Cowboy Joe here with a recapitulation of 12.10 on temperature and thermal energy. Your goal by the end of this video is to be able to distinguish temperature from thermal energy and be able to convert from one temperature scale to the next and define specific heat and calculate problems pertaining to it. Thermal energy. This study is called thermodynamics. The study of heat transformation into other forms of energy is called thermodynamics, and it began in the 18th century. But around 1900, the concepts of thermodynamics were linked to the motion of the atoms and the molecules, replacing the caloric theory with the molecular kinetic theory, which basically helps to explain what's going on here. What happens to the molecules in a balloon? You blow a helium balloon up with helium, there are numerous molecules moving freely in a gas, and that results in many collisions. And the rubber in the balloon is stretched by the repeated pounding from the helium atoms. Each of these billions of helium atoms in a balloon collide with the rubber wall. If you put it in the sunlight, then it will get a little bit larger because the energy from the sun makes each of the gas atoms move faster. Faster moving atoms will result in a greater impulse, a greater force on the balloon and stretching that balloon. And conversely, if you place this balloon in a refrigerator, the balloon is going to get smaller because the lower temperature slows the movement of the helium atoms down, which reduces the force on the outside of the wall, which makes it shrink. So, solids, liquids, and gases are all composed of these atoms and molecules that have a certain amount of energy. And if you add up all of the energy of a certain item, then we call that the energy, the sum of all of the molecular kinetic energy of all the atoms inside a substance is called a thermal energy. We give it the symbol Q. Q is sometimes referred to as heat. So, for example, if you're asked which amount of thermal energy is greater in a hot item or a cold item, the answer, if it's the same amount of mass, would be the hot item. The energy of the hot item, the energy of the particles in a hot item are moving faster, greater energy, more thermal energy. Now, notice how closely this definition is for temperature. This says the total molecular kinetic energy of all the atoms. And this one says the average molecular kinetic energy of all the particles. So the temperature, and this is what they connected in the 1900s, they connected the movement of the particles to the temperature. The faster the particles are moving, the higher the temperature. And then we get into these temperature scales. There's 3 ways to measure temperature. And it all started with Daniel Fahrenheit. He thought the coldest it could be was 0, and then he started putting markings on his glass tube that he blew. They say they blew glass holes. They blew the holes in the glass tubes and filled them with mercury after a lot of trial and error. Galileo was also in the mix of glass making, but he put markings at the freezing point and boiling point of water. And well, as cold as he thought it would get, he started putting marks on there and ended up getting these strange numbers, 32 and 212. And that's what we still use here in America today. 32 degrees Fahrenheit is the freezing temperature of water. 212 is the boiling point of water. Well, Anders Celsius came into the picture and redesigned the thermometer a little bit to make it more realistic. He figured he'd use those 2 special points on there and make it 0 and 100, and he put 100 marks in there. Centigrades is also sometimes called or referred to as a centigrade, centi meaning a hundredth. So he divided it into 100 marks, but this 0 here is his freezing point of water, and this 100 is the boiling point of water on the Celsius scale. So there's 100 marks, otherwise known as centigrade. And then Lord Kelvin came and got rid of all of the negatives and basically did a one-to-one transfer of the numbers. The coldest he could actually, this Anders Celsius could do a backwards line. He could predict the coldest temperatures that we could get to by reducing the energy level to zero on his graph that he created, which allowed him to predict what absolute zero would be. And he's right. And Lord Kelvin came and made that zero. So that 0 point on the Kelvin scale is referred to as absolute zero, and then he numbered up from there. But an increment or an interval from 50 to 51 is the same as one increment over here from 320 to 321. So it's a one-to-one comparison and an easy transfer from Celsius to Kelvin or Kelvin to transfer, or Kelvin to Celsius. You're just adding or subtracting 271.13 degrees to get from this scale to this scale. To get from Celsius to Fahrenheit is a little trickier. It's 9/5 times the temperature in Celsius plus 32, or you can solve this the other way in minus 32 times 5/9, but we'll look at that formula. So first challenge, convert this number into Celsius. So we're going from K to C, K to C, KC, KC negative, minus, I think of the Kansas City Chiefs. So all you're doing is minusing negative minus 273.15. You got 125.2 minus 273 to get the answer. In Celsius, you start with to the tenths. You should end with to the tenths. Now, from Fahrenheit to Celsius is a little bit stickier. You got to deal with that fraction in the formula, and you can use this one, or there's the other one that you can use. But let's just throw it in there. This temperature of Fahrenheit goes into TF. That 30 goes into here. We solve for TC, so minus 32 from both sides puts us to one digit times 5/9, and we have a negative 1 as our answer for this to the nearest one digit. Let's go over one more. How do we go from Fahrenheit to Kelvin? Well, we don't have a formula for that. You can make one up, I guess, but first change the Fahrenheit to Kelvin. So this is 30 degrees Fahrenheit. You throw it into there, and you get the we did this, it's -1. And then we can go from C to K, C to K, check. I think when I put a check in the bank, C to K, I have to add 273. So we're adding 273.15 to that number, to the nearest ones place value, which would be 272. Now we have a little bit of talk on heat here. There's 3 types of heat transfer that I would like to go over. The first is conduction. Conduction is the transfer of kinetic energy when particles actually make contact with each other. When they collide, when you put your hand on a desk, you're making contact. So the energy from the hand goes into the desk. There's convection, and this is the heating throughout a fluid. Convection happens like when you put a pan of water on a stove, the bottom layer is touching it. That gets the bottom layer of water molecules are touching the bottom of the pan. That's heated by conduction, but hot water rises and cooler water goes in and takes its place. That motion of the fluid that is getting heated is what we call convection. And the last type would be radiation. Radiation is the transfer of energy by the electromagnetic waves. So can we say all of the electromagnetic waves? Let's think of a phrase. Red Martians invaded Venus using X-ray guns. So R would be radio waves, right? Red Martians. M would be microwaves. Invaded, I. Infrared, Venus. Invaded Venus would be visible light. Invaded Venus using U, ultraviolet. Using X-rays, X-ray guns is gamma. And notice in the visible light, we got Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. So all that applies there. We're going to talk about specific heat on the next video.